Hello and welcome to the MOOC on Electromagnetics, Applied Electromagnetics for Engineers. In this module, we will first briefly complete the discussion of lumped parameter impedance matching that we are discussing since last couple of modules, and then start looking at the time domain analysis of transmission line circuits. So let us begin by looking at this lumped parameter or lumped circuit impedance matching. We said that lumped circuit impedance matching or lumped element circuit impedance matching is normally taken care at lower frequencies, that is in the range of a few tens to hundreds of megahertz range, or with some luck and with some fabrication expense in the fabrication, you can push this one up to 2 to 3 gigahertz. Beyond this, if you try lumped element circuits for matching problems, then the problem of fabricating the corresponding inductances and capacitances become very expensive. Not that it cannot be done, but it becomes prohibitively expensive. In that case, you simply go over to the transmission line matching or the distributed circuit matching. Okay. However, if you want to perform matching for AM or FM broadcasting elements, lumped element would probably be much more easier, and it is in fact why it is preferred. And it also gives you a lot of flexibility. Solutions are inexpensive, but they do again suffer from the problem of either a narrow band matching or the broadband matching. Most cases would be narrow band. However, you can use multiple such lumped element matching network or matching sections in order to improve the bandwidth of your matching network. Okay. What is the lumped element matching network? It is of course made out of lossless inductances and capacitors. Okay, you can connect these lossless inductors and capacitors in various forms. We will look at only this particular matching network, which is called as the L section matching network. So in the L section matching network, we distinguish two cases. One, there is a susceptance immediately before the load, okay, or immediately after the load, I should say. So this is how the matching network would look. So let me just delineate this matching network in terms of dashed lines. Okay, so this is where the network is going, and let us say this is some R0 or the reference load that you are trying to match. Okay, and ZL is of course the load. In many cases this ZL would be real at these low frequencies. So if you are looking at this, then it would be RL and this would be R0. In many cases this R0 is actually equal to the resistance or internal resistance of the generator RG itself. So this is an L section in which the admittance part comes first, and then you have a series reactance. So you have a susceptance here and a series reactance. There is another case in which the matching network first would have a reactive part, okay, connected to the load. There would be a reactive part, and then there would be the susceptance connected in parallel. So this case of matching network is also usually encountered. So this is again the matching network that we have been designing. The goal of matching network of course is to be able to match this ZL and R0 so that there are no reflections, or there would be maximum power transfer, and of course there would be maximum power transfer. So we can refer to these two cases as say case 2 and case 1, or rather case 1 and case 2. We will only consider the case 1 here. I will leave case 2 as exercises for you to follow up. Okay. So let us look at why case 2 and how to calculate the corresponding values of x and b in case 2 problem. We will solve this problem using Smith chart. Therefore, you can see how the impedances go or transform as we add elements in series and elements in parallel. Remember that when we want to add elements in parallel, you need to convert the impedance Smith chart into an admittance Smith chart. Okay. So let us draw our rudimentary Smith chart over here. Okay. So this is the Smith chart. I hope you have your Smith chart with you so that you can look at the correct values, okay, and practice along with this. So I have the impedance and the reactance circles. As I said, this is just a very rudimentary, very elementary type of a Smith chart that I am drawing. You should have your copy of the Smith chart to facilitate and understand these problems. Understand how to solve these problems. Case 1 is applicable when the load resistance RL, which is what usually happens, or maybe the magnitude of ZL would be greater than Z0 or R0. Z0 is essentially the same as R0, right? So it would be either greater than Z0 or in the real case of R0. In terms of Smith chart, this simply implies that the corresponding load will be within the unit circle. So the one that I am drawing with this green would be the unit circle, and the load would lie inside here. So let us arbitrarily locate the load to be lying at the point where, which is at the point where I have marked a cross. Okay. Now you realize that this is luckily also happens to be, so this black circle on which this blue point is present or blue cross is present also happens to be the constant resistance circle. Now the goal of any impedance matching network is to be transforming from the point X to the point at the origin. Okay. You cannot do that if you keep moving on this constant R circle. Remember, you are only going to add reactances. So suppose you start with this load, okay, let us call this as the load point ZL or the normalized load ZL. Okay. So if you start adding series reactance to it, you won't go anywhere because you are only going along this black circle, and the black circle will not touch the 1 plus jx circle or the unit circle, so that you are able to cancel off the remaining reactances. So here you should not start with a series resistance or the series reactance first. You should convert the load into an admittance, add a required amount of susceptance, so that you bring in the total admittance, or rather you bring in the total impedance in the form of 1 plus jx, and then add a series reactance such that of value minus jx, so that the minus jx will cancel out the plus jx. So let us go back to the circuit that we have drawn. So let me just go back to the circuit here. So this is the circuit. So if this is the load ZL, you first convert the load ZL into the admittance YL. You can also consider normalized loads as we would be, and once you add this susceptance of JB, which will again be normalized. So B divided by R0 will give you the normalized susceptance magnitude value. So once I go over to JB, the total admittance would have been YL bar plus JB, right. So the corresponding impedance, if I look at, so it is not the admittance, if I look at the corresponding impedance now. So this is the admittance that I have. If I transform this impedance, I should then have a transformed impedance of, so let us call this as some ZL prime, to be of the form 1 plus jx, where x is the normalized reactance. Now when I add plus jx or minus jx in this particular case, so if I add a minus jx, again small x denoting the normalization, the impedance seen looking here will be 1 plus j0, and that is, this is the normalized impedance, and therefore we have achieved a match. Okay. So there are two things. First, I need to determine how much normalized susceptance I need to add in parallel to YL, which is the admittance at the load, and how do I move from there onto the unit circle impedance 1 plus jx, so that I can then add the remaining amount of minus jx. So we do this two-step procedure by first converting the load point into an admittance point. In order to do that, I need to draw the constant SWR circle as I have explained to you earlier. So this is not a very nice circle, please forgive me, but once you draw the constant at SWR circle and then obtain a point which we would call as YL bar, that would be the admittance corresponding to this ZL. So it would be located diametrically opposite here. Now from here you need to move in order to obtain this impedance. So first you have to add an amount of JB such that once you obtain the admittance and then transform to the impedance, you should lie on 1 plus jx. How do we do that? Well, remember that any point on the Smith chart can be rotated by lambda by 4, right. If you rotate this impedance or rotate the unit circle by lambda by 4, you will land up with the rotated admittance circle or the admittance circle, which is now going to look like this. Okay. Each point on the rotated unit circle, which corresponds to the admittance, will have a corresponding point as the impedance. Okay. Any point here, when you take the impedance corresponding to this point, so let us call this point as P, and when you take the impedance corresponding to the point P, you would actually land up on the load point, okay, or you land up on the unit circle. So because of that, what we do is we move until, so we move on the constant R circle. So this would have a certain constant R circle. Let me draw that one. Okay, it's again not a very nice drawing, but there would be a constant R circle here. And if I now add, so now I have already obtained the admittance. Now I start moving. Okay, so I move in such a way that I can move either in this way, in which case I am adding positive susceptance, or I can move downwards in the counterclockwise, in which case I would be adding negative susceptance. Okay, so let me choose to add positive susceptance so that I keep moving and I reach the point over here. Let us call this point as some point Q. Okay, what is the nature of the point Q? And please note how we have moved. We have not moved on the SWR circle, we have actually moved on the constant R circle corresponding to the point YL bar. So after moving I reach Q. I know that point Q must correspond to a point on the unit circle. Okay, so I can go and find out what would that point be by having a line passing through from Q origin and landing on the unit circle, so which is the unit circle over here. Now this corresponds to ZL bar prime, and you notice that ZL bar prime in this case happens to be of the form 1 minus Jx, because it is now lying in the lower hemisphere. The imaginary part would be negative here. Now from this side, if you start moving by adding a certain amount of reactance, which is the amount of x that you want to add, you would reach the center of the chart and then you would have obtained matching. How much susceptance you have added? You can first note down what is the coordinates of YL bar, or rather coordinates of YL, okay, and then you have moved along the constant R circle by this amount. Okay, subtract the reactance at this point and subtract the reactance at YL bar, and you would obtain what is the amount of susceptance you have added. In this case, please note that the susceptance to be added is positive, the reactance to be added is also positive. This is ZL bar, but if you add to this plus Jx, then you will get ZL double bar, which is equal to 1 plus J0, which corresponds to the match condition. Okay. So you need to add positive susceptance and positive value of the reactance. Consider the inductor. What is the reactance of this inductor? It is J2 pi FL. This is the actual reactance, but then you need to divide this actual reactance by the corresponding value of impedance, right, in order to normalize this. So J omega L is the reactance of an inductor, and then divide by Z0 will give me the corresponding normalized value. So if you equate these two and solve for L, you will be able to easily find out what is the required value of the inductance, which gives you a corresponding reactance of plus Jx. Similarly, for positive susceptance, we know that a capacitor will have a positive susceptance. So Jb would correspond to J2 pi Fc, right. So again, solving these two by equating these two, sorry, this is just J2 pi Fc, but this has to be normalized with respect to the admittance. Please note that inductive reactances are normalized by Z0, capacitive susceptances are normalized by the admittance Y0. Okay. So now equate these two, find out the expression for C, or find out the value for C. Okay. If you want to get some practice with this, you can start by this example. Assume that the normalized load that you are trying to match is 2 plus J1, okay, and assume a frequency of about 135 megahertz. By following this procedure, determine the L and the C values, and of course determine what is the structure of the matching network. In this case, please remember, B turned out to be positive, X turned out to be positive. Positive reactance means inductor. So the matching network would have a capacitor of the value C that you have found out, and it would have an inductor whose value you would find out from equating these two expressions. Okay, so Jx and J2 pi FL by Z0. So this is your matching network. Unfortunately, this matching network that we have obtained is not broadband, because if you start looking at its frequency response, at the desired frequency they would have some value, they would be they would peak at the desired value. But what happens when the frequency is very large? Then this inductance will have a reactance which would be very large, the capacitive reactance shorts out, this becomes an open circuit, and the response actually drops down to 0. Okay. So, on the other side it will not drop down to 0, it would be slightly asymmetric, because at very low frequencies the inductor will act like a short circuit and the capacitor will act like an open circuit. So, this is the frequency response of this particular matching network. Okay. So, this completes our discussion on matching networks. Thank you.